Chemical Equilibrium, Part 7, Le Chatelier's Principle. Le Chatelier's principle is that if a system at equilibrium is distorted by a change in either concentration or temperature or pressure, the system will shift its equilibrium position to counter the effect of that disturbance. Let's take a look at each one of those in turn, starting with concentration. If a substance is added to a system that's at equilibrium, the system reacts to consume some of that substance. So we have two substances on the left in equilibrium with this one substance on the right. And then we add some of this substance. That disturbs the equilibrium, and the substances on the left will react to produce more of that product on the right. A new equilibrium will be established. We'll have less of this first substance than we initially had. We'll have a little bit more of this second substance than we initially had. We added some to it. But we'll also have a little bit more of this product than we initially had because some of these chemicals reacted to produce that. Now we can do that in reverse too. If a substance is removed from a system at equilibrium, the system shifts to produce more of that substance. So if we add a substance to an equilibrium, the equilibrium shifts away from that addition. And if we remove a substance from an equilibrium, the equilibrium shifts towards that addition, or that removal rather. So let's say that you mowed your lawn and you let your lawnmower sit for a little bit, and an equilibrium establishes in the fuel tank between the liquid fuel and the gaseous vapor above that fuel, inside the closed tank. Then you decide that you're going to store your lawnmower in the shed, and you just want to make sure that you have the fuel tank filled up for next time. So you open the cap, and when you do that, some of the gaseous fuel, some of that vapor escapes from the tank. Let's say you decide there's enough fuel in there, so you put the cap back on. Since some of that gaseous fuel escaped from the tank, a new equilibrium would have to be reestablished, where some of the liquid fuel would evaporate and fill the space above it inside the tank. So you can remove substances in all different ways. Let's take a look at pressure. Now this is really important for gaseous equilibria. At a constant temperature, reducing the volume of a gaseous equilibrium mixture, thereby increasing the pressure in a closed container, causes the system to shift in a direction that reduces the number of moles of gas. So let's say that we have a sample here with a certain initial volume, and then we put pressure on that, and we make the container smaller and don't let any of the gas escape. So now we have less volume. What's going to happen there is the system will shift to the direction of fewer moles. We'll take a look at some examples in a little bit. Also, if the volume of the gaseous equation mixture is increased such that the pressure is reduced, then the system shifts in a direction that increases the number of moles of gas. So continuing on with pressure, does volume have to change to cause a pressure change? And the answer to that is yes. Now you might think, well, you could change the pressure in some different ways, like you could add more of a gaseous reactant, and if you did that, that would increase the pressure, right? But really, what you would be doing is just changing the concentration. And we've already considered what a change in concentration will do. Another thing you could do is say, well, how about adding a non-reactive gas, say like argon gas? Well, that does not change the partial pressures of the reactants. And remember that the equilibrium constant is calculated, Kp is calculated using partial pressures. So since adding a gas would change the total pressure of the mixture, but not the partial pressure of the other gases in the mixture, there is no change in the equilibrium position as a result. So, a few important points here. changes in concentration do not change the equilibrium constant. In fact, the shifts that we see as a result of Le Chatelier's principle are because we want to keep that equilibrium constant the same. And also, same goes for changes in pressure. Changes in pressure will not change the equilibrium constant. It will stay constant. Now, temperature, on the other hand, that's our third factor here. Temperature does cause the equilibrium constant to change. We can say that KEQ, whether it's expressed as KC or KP, is temperature dependent. If the temperature of a system at equilibrium is increased, the system reacts as if we added a reactant to the endothermic reaction or a product to an exothermic reaction. The equilibrium shifts as if heat were a chemical in the equation. So let's take a look at these. Here's an endothermic reaction. Remember that an endothermic reaction is when delta H is positive, it's greater than 0. So we would say that the heat is added to the reactant side. So the reactants plus heat are in equilibrium with the products. And you can treat heat, for the purposes of Le Chatelier's principle, as if it were a chemical. So increasing the temperature would mean adding heat. And if you add heat, the equilibrium would shift to the right, away from that addition. And if you decrease temperature, well, that would be decreasing heat, taking that heat out. So if you took a chemical away from the left-hand side, the equilibrium would shift to the left. So we just treat heat as if it were a chemical. Remember that in endothermic reactions, heat is added to the chemical, so it's on the reactant side. Now, increasing the temperature will cause an increase in the equilibrium constant value. And decreasing the temperature will cause a decrease in the equilibrium constant value. Remember that when we write the equilibrium constant expression, we have products over reactants. So in an endothermic reaction, increasing the temperature, adding heat, would shift it to the product side. That would make KEQ bigger. Decreasing temperature would shift the equilibrium to the reactant side, and since reactants is in the denominator of the KEQ expression, it would make KEQ smaller. So for endothermic reactions, increasing temperature increases the value of KEQ, decreasing temperature decreases the value of KEQ. Now let's take a look at exothermic reactions. These are reactions where delta H is negative. So heat is leaving the system being the chemicals, and going into the surroundings. That means that when we write the chemical reaction out, even this equilibrium reaction, we put heat on the right-hand side. So increasing temperature, that means increasing heat. We're putting heat on this side. That's going to make the reaction shift left. If the reaction shifts left, if the reactants are favored, that's going to make the equilibrium constant smaller. Again, remember the equilibrium constant is calculated with products over reactants. So if we shift the equilibrium towards the reactants, KEQ is going to decrease. With an exothermic reaction, increasing temperature makes KEQ get smaller. And then we see the reverse. If you decrease temperature, that means we're taking heat out of this side of the reaction, right? Because decreasing temperature is removing heat. If we remove heat from the product side, the equilibrium would shift towards the products. And when it shifts towards the products, the numerator in the KEQ expression would get bigger, and that would make KEQ bigger. So with endothermic reactions, increasing temperature increases KEQ, decreasing temperature decreases KEQ. With exothermic reactions, increasing temperature decreases KEQ, and decreasing temperature increases KEQ. Let's take a look at some example problems putting Le Chatelier's principle into practice. Let's say we have this equation, and this is an endothermic equation because delta H naught, so the change in enthalpy under standard conditions, is 58.0 kilojoules. It's a positive value. And anytime delta H is greater than 0, that's endothermic. So let's go ahead and write that out with the heat on the reactant side. And let's answer a bunch of questions in relation to in which direction will the equilibrium shift when A, N2O4 is added. Well, if we add a chemical to an equilibrium, it's going to shift away from that addition, so it would shift to the right. And that would be done to decrease the concentration of the added N2O4. What if we, B here, removed NO2? Well, then the equilibrium would again shift to the right to increase the concentration of the NO2 that was removed. How about C? We add N2, which is a non-reactive gas in this reaction. Since it's not part of the reaction, it's non-reactive here. Well, that would have no effect. The total pressure would go up, but the partial pressures of the reagents would remain unaffected. So that means that since the Kp is calculated with partial pressures, if they don't change, Kp doesn't change. The equilibrium doesn't shift in one way or another. I guess Kp wouldn't change in any case, but the equilibrium doesn't shift because the partial pressures aren't affected. What if we increase the volume, the overall volume of the vessel in which these gases are at equilibrium? So we increase the volume of the gases. Increasing the volume would shift the equilibrium to the right. The system shifts in a direction that occupies more volume when we increase the volume of the container. In other words, it will shift in the direction where there are more gaseous particles. And here we have 2 moles of gas, and here we have 1 mole of gas. So if we make more room available, the gases will expand and fill up that space. When they expand, we're going to favor the side of the equation that has more gaseous chemicals, more moles of gaseous chemicals. All right, what if we decrease the temperature? Well, decreasing the temperature here in E, this would be taking heat away. So if we remove heat, just like removing any chemical, the equilibrium would shift to the left. Decreasing temperature is removing heat, so the equilibrium shifts to the left because we're treating heat as if it were a chemical or a reagent. Let's take a look at another example. Let's say that we have this equilibrium reaction, and we can look up the standard heats of formation or standard enthalpies of formation. So let's say we go to a table and look that up for NH3 gas, and we find it to be negative 46.19 kilojoules per mole. Let's use that to calculate the delta H naught of this reaction, and then comment on how the equilibrium would shift with changing temperature. So we can say that for this reaction, where we're producing 1 mole of NH3 from its elements, that would be a formation reaction if it were done under standard conditions. Now remember that we covered this in thermochemistry. A formation reaction is when 1 mole of a product is formed from its constituent elements in their most stable states under standard conditions. So the most stable state of nitrogen is gas, and the most stable state of hydrogen is gas. And delta HF naught, in other words, the standard enthalpy of a formation reaction of elements in their most stable state, is 0. And that's by convention. So we assume that the elements are already formed. And then standard conditions is when temperature is 25 degrees Celsius and pressure is 1 bar. And 1 bar is just about 1 atmosphere. So since we know that the delta HF naught for NH3 gas, producing 1 mole of NH3 gas, is negative 46.19, and this reaction is producing 2 moles of NH3, you might remember that we would have to take 2 moles of NH3 multiplied by that negative 46.19 kilojoules per mole, and that would give us negative 92.38 kilojoules. That would be the delta H of reaction. And that's really a topic that was covered back in that thermochemistry. Now, because this is a negative value, that's exothermic. So that means we would write the heat on the right-hand side, on the product side. That means increasing temperature would be adding heat, and that would shift the equilibrium away from that addition, so it would shift the equilibrium to the left. And decreasing temperature would be taking away heat. If we removed that heat from that side, that would be like removing a chemical. The equilibrium would shift towards that side, towards the right, to try to make up for that removal of that chemical or that heat there. All right, so let's move on and talk about how a catalyst can have an effect. Adding a catalyst speeds up a reaction. It increases the reaction rate, but it does so in both the forward and reverse reactions. So both rate constants, the forward and reverse rate constant, get bigger, and they get equally bigger. So remember that the equilibrium constant is really just a ratio of the reverse rate constant divided by the forward rate constant. So the equilibrium constant is a ratio of those two constants, and if those two constants change, but they change equally, the equilibrium constant doesn't change. So in other words, if the reverse rate constant gets twice as big and the forward rate constant gets twice as big, the two multiplier on the top and the bottom cancel out, and KEQ stays the same. So KEQ stays constant, but the equilibrium is established more quickly because we have bigger rate constants and a faster rate. That's important to know, that we'll get to the equilibrium at the same KEQ, but it'll happen faster. Let's take a look at several different examples around this equilibrium reaction. In part A, let's say that we have Kp is equal to 14.1 at 800 degrees Celsius, or 1073 Kelvin. Let's calculate the partial pressure of H2O, CO, and H2 at equilibrium. Given that the initial amount of moles of H2O was 0.1 moles and the volume of the container is 1 liter. So first of all, the initial concentration of H2O is 0.1 moles divided by 1 liter, or 0.1 molarity. We can use PV equals nRT and rearrange it so we get P is equal to N over V times RT. N over V is the same as molar concentration, so the initial partial pressure of H2O initially is equal to the concentration times the ideal gas constant times the Kelvin temperature. So we have this 0.1 molar concentration. Here's the ideal gas constant, 0.08206 atmosphere liter over mole Kelvin, and we have 1073 Kelvin. Solve that, and we end up with 8.81 atmospheres. Now here's a little bit of a shorter way to do it. You can just say that P is equal to N over V times RT. We derive that again from the ideal gas law. Then plug in the moles and the volume, so 0.1 moles and 1 liter for N and V, and multiply out by everything else, and you get 8.81. All right, so then let's do a Rice table here. Here's our reaction. We have our initial conditions. This is solid. We have 8.81 atmospheres in terms of partial pressure of H2O, and 0 atmospheres of these products. So this reaction is just getting going. And the change in the chemicals is a 1-to-1 to 1-to-1 ratio. So it's negative X to negative X to positive X to positive X. So we're going to diminish some of these reactants and produce some of these products. That's why these are negative and these are positive. We're starting with some reactants and no products here. All right, so then combine the initial and the change, and we get the equilibrium conditions. So whatever amount of solid carbon we started with minus X would give us the equilibrium amount of carbon that we have there. 8.81 atmospheres minus X is the equilibrium amount of H2O, and that would be the partial pressure at equilibrium. And then 0 plus X is just X, and 0 plus X is X. So X atmospheres and X atmospheres would be the partial pressure of CO and H2. Okay, so then remember that when we write Kp, whenever we write any equilibrium constant, we omit pure solids and pure liquids, so the carbon is not involved. So we have the partial pressure of CO and H2 on top, and the partial pressure of H2O on the bottom. Let's plug in these equilibrium values from here, from this Rice table. So CO has an equilibrium value of X, H2 is X, and H2O is 8.81 minus X. So we can take this quantity and multiply it by 14.1 here, and then X times X is X squared. Let's distribute that 14.1 into those parentheses, into that value in the parentheses, and we get this on the left, and X squared stays on the right. And then rearrange it so it looks like this, and we can plug it into the quadratic formula, the quadratic equation. When we do that, we end up with two values, 6.14 or negative 20.2. Well, it can't be a negative number. You can't have negative concentrations. So X equals 6.14. So at equilibrium, the pressure of the CO is 6.14 atmospheres. The pressure of the H2 is 6.14 atmospheres. And the pressure at equilibrium for H2O is 8.81 minus X, 8.81 minus 6.14, or 2.67 atmospheres. All right, so then using that same equilibrium equation, what's the minimum amount of carbon, that solid carbon, that's needed to achieve equilibrium at 800 degrees Celsius? Well, carbon is solid, so we're going to measure it with mass. So we're going to calculate the mass when it says minimum amount here. Let's find the mass. So we know that X, the amount of water that was needed to reach equilibrium, and we could see that from this Rice table, right? That this gaseous water that was needed to reach equilibrium was X. So we had to decrease the amount of water by X amount. That was the amount that was needed to reach equilibrium, 6.14 atmospheres. So let's convert that to the partial pressure of water. Oh, I'm sorry, convert this partial pressure, 6.14 atmospheres, to moles of water using PV equals nRT. So rearrange PV equals nRT and solve for N. It's equal to PV over RT. Plug in the partial pressure of the water, 6.14 atmospheres. The volume of the container is equal to the volume of any gas in the container, so 1 liter. Remember, gases occupy the volume of the container. Divide by the ideal gas constant, R, and the temperature, 800 degrees Celsius, is 1073. You have to use Kelvin for temperature. We solve that this is 0.0697 moles of water that was needed to reach equilibrium. Now, from the balanced equation, we can see that the moles of water equal the moles of carbon. Right? If we needed X moles of water to reach equilibrium, we need X moles of carbon to reach equilibrium. That would be the minimum moles of carbon to reach equilibrium. So, if that's how many moles of water is needed to reach equilibrium, that's the same for carbon. We convert that into grams, and it turns out to be 0.838 grams of carbon would be needed to reach equilibrium in that reaction at 800 degrees Celsius. So another question, this is part C for that same equation. What is the total pressure at equilibrium in the vessel? Well, that's easy. We just add up the partial pressure of all the gases. So the partial pressure of the water and the CO and the H2. So 2.67, 6.14, and 6.14 all total out to be 14.95 atmospheres. Notice we're doing that for gases in the reaction, not the solid carbon. Of course, a solid wouldn't have a partial pressure as a gas because solid's not volatile, it's not producing gas. Okay, so then D, another question regarding that same equilibrium reaction. Since Kp was 14.1 at 800 degrees Celsius, if we cool it off to 25 degrees Celsius, Kp gets really small, 1.7 times 10 to the negative 21st power. So just to emphasize that, that's a negative there. That's going to make it a really, really tiny equilibrium constant at that temperature. So what does that tell us? Is the reaction exothermic or endothermic? Now, rather than try to memorize all that stuff, I think it's easiest just to figure it out as you go. So Kp, any equilibrium expression, equilibrium constant expression, is always calculated with products over reactants. So decreasing the temperature from 800 to 25 caused a decrease in Kp. It went from 14.1 to 1.7 times 10 to the negative 21. That's a pretty big decrease. So we can say that the reaction must shift in a way to make Kp smaller when the temperature goes down. Well, that means it has to make the reactant side larger, right? It has to shift away from the products and make the products smaller and make the reactants larger for Kp to get smaller. So the reactants must be favored at that lower temperature. That means the heat is on the reactant side. Removing that heat from the reactant side shifts the equilibrium to the reactant side. It shifts it to the left. Well, that means the reaction's endothermic when the heat's on the reactant side. Okay, last question regarding that equilibrium reaction that we've been dealing with. This is part E. To produce the maximum amount of CO and H2 gases, should the pressure of the system be increased or decreased? Well, the answer is it should be decreased. Decreasing pressure, that is to say increasing volume, causes the equilibrium to shift in the direction where there are more moles of gas. Of course, more moles of gas would occupy more volume. So in this reaction, there's CO as a gas and H2 as a gas. That's 2 moles of gas on the right. And the only gas on the left is H2O. That's 1 mole of gas on the left. So when we decrease pressure, right, increasing volume, the equilibrium is going to shift where it accommodates more pressure, where more gaseous particles can occupy that larger volume. Again, decreasing pressure causes an increase, or would be caused by an increase in volume. So decreasing pressure will increase the production of CO and H2. That's it for Le Chatelier's principle.